Now, how are we going to find to calculate the value of K, which is rate constant? So what's going to happen here is, using the figures that you have, for instance, using what you have on the table, we're going to find to say, if you're going to use experiment number 1, you go with experiment number 1, which means you go with ammonium, nitrate, and also their initials. If you're going to fix experiment 2, you go with ammonia, nitrate, ammonium nitrate, and also initialate. Just like that, also experiment number 3. So what's going to happen, the same number, if you're going to find with the experiment number 1, the rate constant for experiment number 1 should be equal to experiment number 2, experiment number 3. That's what that means. So what's going to happen if you see very much properly? Shall we proceed? Okay. So for instance, if we go with experiment number 1, which means nitrate, ammonium are going to have 0.100 molar. Same applies with nitrate. Same applies with the initial rate. So which means we are lying in experiment number 2. So shall we go ahead? So the rate, we have 1.35 times 10 times 10 exponential 7. Then what about rate constant? That's the one that you're calculating. Now, what about ammonia? Notice a positive charge, being a large with valence of 1. So ammonia, we have 0.100 molar, as in the concentration of ammonia. What about nitrate? So for nitrate, we have 0.005 molar, lying in the same position. That means what I'm trying to say is this. Experiment number 1, we have 0.100 molar, nitrate 0.1005 molar, initial rate 1.35 times 10 raised to negative 7 molar per second. Okay, shall we proceed? Shall we? Let's go. Our studied rate is equal to constant, the concentration of ammonia, times the concentration of nitrate. We all know to say their order of the reaction is 1. Ammonia, the concentration of ammonium is 1, the concentration of nitrate is 1. So what's going to happen if I go to the nitrate here? Well, let me say the constant here. So you can try to make constants as substitute the formula. So nitrate, the concentration of ammonium, and also the concentration of nitrate. Same applies. The concentration of ammonia and also the concentration of nitrate. So we go, and we remain with rate constant, which is equal to rate divided by the concentration of ammonia and also nitrate. So what is the rate? We're talking about the rate as in experiment number 1. We have 1.35 times 10 exponential negative 7 divided by, for ammonium, the concentration of 0.100 molar, and also for nitrate, we have 0.005 molar. Then, what's the forward after this? We say rate constant 1.5 times 10 exponential negative 7 molar per second. You get your calculator, you punch it here, you say 0 . You say 0.10 0.10 0 times 0.005. What's our answer? This one means our answer. So we're going to have 5.0 times 10 exponential negative 4, and our rate constant is equal to, you say 1.15 exponential negative 7 divided by 5.0 exponential negative 4. What's your answer? 2.0 times 10 exponential negative what? 4. So, if you see very much properly, having one order as in first order of the reaction, we all know to say it's going to contain, how are you going to calculate, or how are you going to put the units here? So it's the first order of the reaction. What are you going to do? We all know to say, we're going to have molar over second times molar over seconds. Or should we try to forget about that? Shall we? Let's go. We said, okay, let's go ahead before we forget about it, just to calculate the unit. So what we're going to do, we say, we know about the reciprocal of molar there, times molar, as we are talking about the first order of the reaction divided by second. If we add in the second, or for instance, if you add the second order of the reaction, we're going to put 2m, or let me say m squared there. But as in the first, you put 1m, then I get the reciprocal of 1. So what's going to happen? We're going to have this m and this m as in molar gone. Then we remain with it, the reciprocal of a second. So that means to say the units here are going to have second there, as in the reciprocal of a second. So this is the rate constant. So that shows to say, for instance, if you try to calculate, you go with experiment number 2, you get the nitrate, ammonium, in experiment number 2, the concentration of ammonium in concentration number 2. Same applies with the nitrate concentration in experiment number 2, and also initial rate in explanation number 2. You're going to have exact answer. If you do not have exact answer or same answer, that means to say it is wrong. Thank you very much. Let's try to progress to another question. Shall we? Let's go. So what's going to happen here, a big part of chemical kinetics. So I've got what we call orders of the reaction. So I've got first order of the reaction. In fact, we have zero order of the reaction. So this one's supposed to be zero order of the reaction. Not only that, this is supposed to be second order of the reaction. Also, this one's supposed to be, this one first order of the reaction. Then this one's supposed to be second order of the reaction. So I have zero order of the reaction, first order of the reaction, second order reaction. So altogether, they're supposed to be 3. So the zero order of the reaction, that's got the concentration, let me say, the equation, which is, if you see very much proper, this is just a combination of differentiation and also integration. Should I say, we're only focusing in the expansion of integration. So that means to say, this is just an explanation of how a rate, a law, or how a rate depend, or rate of the reaction depend on the concentration of the reactant moving with time. So if you see very much properly, I've got the constant and also time. If you see very much properly, also we're only dealing with the reactant. So that clearly indicator says a combination of what reactant, or let me say combination of differentiation and also integration. So should I just get a concept a little bit out of it? Yes. So that is the first order of the reaction, zero order of the reaction equation. And also I've got second, first order of the reaction equation, which is this one. And also we have a second order. So zero order, first order, second order of the reaction. Now, After that, what's going to happen? These are some of the formulas you're supposed to put in mind. Now, shall we get now what you call half-life? What is half-life? What is half-life? So this is the time taken of the reactant, or the time taken of which the concentration of the reactant decreases by the half of its initial, or by the half of its initial value. So what's going to happen, for instance, if you try to get the zero order of the reaction, which is the concentration of the reactant would depend on time, is equal to the negative constant of moving with time plus your initial concentration. Now, if you see very much what I talk about half-life, we say that is half-life, we're talking about the time taken of which the concentration of reactant decreases by half of its what? Initial value. So that means to say everything has to change since what